Hello, everyone, and welcome to this episode. Today, we're going to be speeding through some multiple choice questions in regard to AP Chemistry Unit 7, Chemical Equilibrium, specifically General Equilibrium. I found a whole bunch of questions, and I want to go through a whole bunch of questions, but each one, they're pretty dense and they take a little bit of time. So I've separated them into categories for separate videos. Today, we're going to be doing General Equilibrium, but you can look ahead to other videos on manipulating equilibrium constants. That's a big deal on the AP Chemistry exam. Le Chatelier's principle and solubility equilibria, which is now covered in Unit 7. It used to be in part of a different unit. And then I found some challenging questions that are sometimes put on the exam to sort of separate the test takers from each other. And I want to treat those in a separate video because they take a little bit longer and are a little more in depth. So in this video, though, we're going to do some general equilibrium, and if all goes according to plan, in a few minutes, you'll have a good idea of the types of questions you might see on the AP Chemistry exam. So let's get started. The purpose of this video is to graze around and see a whole bunch of different types of equilibrium questions that you might be asked, all the different ways that equilibrium concepts could be presented to you on an AP Chemistry exam or another chemistry exam. And there's a lot of words, and we're going to try to balance moving quickly through them, but also adding a little bit of description or explanation to them. So a good strategy for you might be to have a short rein on the pause button, just so when a new question comes up, you can just quickly pause it, see what you think, maybe read through the whole thing, and then we'll get back to the actual answers. So that's something that you can decide if you want to do or not. We're going to start with this one, which has a graph showing things getting to equilibrium. We have hydrogen and nitrogen gas making ammonia gas. The delta H was negative 92 kilojoules per mole. I don't think that matters here. But the diagram is shown here, and the question is, which of the following was true for the system between time t1 and t2? So during those two times, everything was pretty constant, which tells me that the system has reached equilibrium. And the answer that goes along with that the best is that the rates of the forward and reverse reactions were equal. That's pretty much in the definition of dynamic equilibrium. So that's that. Here's a different one, but not in graphical form. It's more in tabular form. So we have time in minutes, x and xy. So here we have x going down and xy going up. And that's a 1-to-1 ratio. So you'll see them kind of going up and down at the same rate for each part. In an experiment, X and Y were combined in a rigid container at constant temperature and allowed to react as shown in the equation above. The table provides the data collected during the experiment. Based on the data, which of the following claims is most likely correct? So I chose B here already because somewhere between 75 and 155, you'll notice that the concentration stopped changing. Okay, again, in tabular form, this could be on a graph as well. So from here on, we don't see any change. Does that mean it actually started equilibrium at 155? Well, we don't know that because we don't know the instant that we just know that sometime between 75 and 155, it reached that and then it stayed there. So that would be the correct answer with that one. All right, here's one. We have a table with some methanol and some ethanol in it. Equimolar samples were placed in separate previously evacuated containers and kept at 300 Kelvin. In both vessels, liquid observed to remain present in the bottom of the container at all times. So we're actually evaporating and unevaporating or condensing. The change in pressure inside the vessel is shown below. This is the methanol vessel. And it says here the value of Kp for the evaporation of methanol at 300 K is closest to. So what do we do there? So you might get to a question like this and be like, oh, Kp. So I might have to write the equilibrium constant expression. So that would be equal to the pressure of methanol vapor, all right, because it's evaporating, over, so this is the gas form, over the pressure of methanol liquid form. All right, and you might get to this point and think, oh gosh, I don't have enough information for this. Well, it helps to remember and keep your eyes out for those liquids and solids, which do not actually get included into the equilibrium constant expressions. So Kp is actually simply the pressure of the methanol, which in this case got up to 0.196, which is closest to 0.2, and I can pick my answer there. So you had to kind of mentally keep your eyes out for stuff in that one. A little tricky on that one. Okay, next one. Here we have N2O4 making two NO2s. Kp is 3 at 70 degrees Celsius. This is colorless. That's brown. This is a demo that I do in class. A mixture of N2O2 and N2O4 is placed in a glass tube and allowed to reach equilibrium. If the pressure of N2O4 is 0.64, what is the pressure of NO2? So here, again, let's just write the Kp expression. Pressure of NO2, and that's going to be squared. Pressure of N2O4. Okay, so that's our Kp expression. We've been told Kp is 3, and we need to know the pressure of NO2, which is the top part, and that's squared again, don't miss that, over 0.64 atmospheres. So when I do the math and I solve for that, I get that the pressure of NO2, remember to square root it, is 1.4 atmospheres. So it's a fairly straightforward plugging in numbers and solving for one of the components on that. Our next one gets at the relative amounts of reactants and products as things approach equilibrium. So we have the equilibrium equation up here. I'm going to try to generalize that when I say that. The synthesis of methanol from carbon monoxide and hydrogen is represented by that equation. And a 1 mole sample of CO and a 1 mole sample of H2 are pumped into a rigid container at 483 Kelvin. Which of the following is true at equilibrium? Pay attention to these types of questions and which one is going to go down or up faster than the other ones. Note we have H2 and CO being mentioned, all three of them being mentioned. I do note that there's a 1-to-2 ratio here. So as this moves to the right and gets to equilibrium, the hydrogen is going to go down faster than the carbon monoxide is going to go down because it's twice as much. And so therefore, the hydrogen has to be less than the carbon monoxide as it approaches equilibrium. So there's that. All right, next one is kind of the similar thing. So we have a different equation, and it says equal number of moles of HCl and O2 are in a closed system and allowed to reach equilibrium as represented. Which of the following must be true at equilibrium? Our choices are HCl must be less than Cl2, O2 must be greater than HCl, and Cl2 must equal H2O. So I'm thinking, looking at the mole ratios, take a moment and see if you can guess which combination of 1, 2, and 3 is correct. Pause for a couple of seconds. This is similar to our last question, and if you guessed or said that letter C is correct, then good job. You noticed that this goes down faster than this, and these two go up at the same time. We don't know for sure whether HCl is less than Cl2. We don't know how far it's going to the right and what the equilibrium constant. So that's uncertain. It might be true. It might not be, though. These two have to be true. Sometimes you have to do some quick math, either in your head or on your paper, to answer these questions. So we have, again, an equilibrium reaction. 2 moles each of hydrogen, iodine, and HI. They're all placed in a rigid container. And we want to know what will happen as the system moves toward equilibrium. Here's where we have to use the value of Q, the reaction quotient. So what we have to do is plug in what we have so far, 2 moles in 1 liter container, so that's 2 moles per liter. We're going to have 2 moles per liter squared over 2 moles per liter and 2 moles per liter. I'm doing this in my head. That gets me 2 squared over 2 squared. That's going to be a Q value of 1. We're told the K value is 50. So to get to K, we need to go to the right and make more of the products, and that means that more HI is going to form as that happens. So you could have also done it on paper. And gotten your K value that way. Either way, it doesn't take very long. And remember, you have like a minute and a half per question on the AP exam. Here's another one where you're going to have to do the Q value again. And so it's a very similar question. They kind of recycled this one from year to year. So take a moment and see if you can solve this one. And again, we have the same reaction. So we have equimolar samples. Does it matter how many moles? No, because they're in the same size container. So we're going to have some concentration squared over the same concentration squared. It's again going to be an equilibrium value or Q value of 1. It's going to shift to the right. Now the wording is slightly different. More HI will form because Q is less than K. So they added that in there as maybe a hindrance or a help, depending on how you think of that. But that one is done. Okay, so a certain gas, XY, generic here, decomposes as represented by the equation above. I see that the Kp value is 230. Okay, and a sample of each of the three gases is put into a previously evacuated container. The initial partial pressures are shown in the table below. So again, I need to sort of find a Q value and see what's going to happen. So Q is going to be equal to X, so 0.2 times 2 over 0.010 squared. And that gets me a Q value. But because we're going to be dividing by 0.01 squared, which is 0.0001, this is going to end up being quite a large Q value. And so it's actually going to shift back to the left. And the reaction will form more reactant. It's going to be a Q value bigger than 230 on that one. All right, here's one based on a reaction that we did in one of our labs. The reaction of iron and thiocyanate ion to make this complex ion with a 2+ charge. The value of the equilibrium constant is 240 at 25 degrees Celsius. From this information, the correct deductions about the reaction include which of the following? All right, and they give us the reaction is quite rapid, the product is favored over the reactants, and the reaction is endothermic. Okay, so what can we conclude? Is it rapid? Well, I think it is actually pretty rapid, but that doesn't depend on the K value. Okay, so there's a distractor here. The K value tells you the ratio of the products over reactants. It doesn't tell you how fast it gets there, so you can't assume that. We also don't know yet if it's endothermic or not. We would have to know the equilibrium constant at a different temperature in order to see where it's going. So I don't know that either. The only one I actually do know is that the products are favored because you have a pretty large equilibrium constant. So careful of those distractors. Okay, here our next question is a particle diagram. And so this is another way to show things getting to equilibrium. So the particle diagram shows the changes that take place when X and Y are placed in a rigid container, making XY. Okay, so which of the following is a characteristic of a system at equilibrium that is best represented by the particle diagram? So I always tell my students, when you see diagrams like this, start counting. Start counting atoms and molecules immediately because it's probably doing something about how many there are. So here they have all separate. Here we have 2 molecules of product. Here we have 3 molecules of product. And then there's 3 molecules from then on. And so that tells me that somewhere between 100 and 200, there is no change and it reached equilibrium there. And so there are no observable changes in the amounts of reactants and products, which is a characteristic of a system at equilibrium. All right. Next one. In 1 molar hydrochloric acid is nearly 100% dissociated as represented by the equation above. So it's nearly 100%. Which of the following helps explain why in 0.01 molar HCN, less than 1% of the HCN has dissociated in a similar manner? And the answer here is that it's all about the equilibrium constant. Equilibrium constant of HCN is much smaller than that for HCl, and so it just doesn't dissociate quite as much, nearly as much actually. And here's another related question. So this might be our pause the video moment for this segment. At night, an equilibrium reaction between 2 different nitrogen compounds generates N2O5 in the atmosphere as represented below. I'm not sure why it happens only at night, but they tell us that it does. The equilibrium constant is there. A mixture of NO3 and a 10-fold excess of NO2 are placed inside a rigid container at constant temperature. So we got a little bit of this and a lot of that it's telling us. Which of the following provides a correct comparison of the equilibrium concentrations of these chemical species and why? Take a moment, pause the video, read through the choices, and see what you think. All right, and if you picked letter D, then congratulations. The concentration of N2O5 must be really small in comparison to this one because that's a very tiny equilibrium constant, and the formation of products is not favored at equilibrium. So if you got that, good job. All right, just a couple more to finish up this video. A 1 mole sample of X, there it is, and a 1 mole sample of Q are introduced into an evacuated container at equilibrium. Which of the following is true about the concentrations of the gases? Again, pause the video if I skip over things in the interest of speed. 10-liter container and 1 mole of each. So what's true? That ends up being that letter C is going to be true. And I chose that because R and Z are going to have to be the same. They're starting at 0 and they're going to go up the same amount. No matter what the amount is, they're going in a 1-to-1 ratio. And because it's a very large equilibrium constant, it's going to go far to the right, leaving very little Q at the end. So the Q is going to be smaller than R and Z, which are equal to each other. All right, and we have one more. This will pause the video moment. This is cis dichloroethene, and this is trans dichloroethene. And we have the two isomers of there, and the equilibrium constant is trying to be determined. And the table provides data collection in an experiment to determine its equilibrium constant. In a second experiment done at the same temperature, Z is now going to be 1 atmosphere, 1 mole per liter. Which of the following is the approximate equilibrium concentration of Y in the second experiment, and why? Take a moment, pause the video, and see if you can solve this one. All right, and if you chose letter B, then congratulations. So it's a very simple equilibrium. There's only one of those on the top and one of those on the bottom. There's no squares or cubes or anything like that. So we just have this ratio 0.8 to 1.2, 0.8 over 1.2. So if this goes up to 1, this is going to have to go up proportionally, and we're estimating around 1.5. It's probably not exactly that, but it's close to 1.5. All right, there, we completed our first little segment on general equilibrium problems, and you can look ahead toward more videos on the other categories of problems, like manipulating equilibrium constants, Le Chatelier's principle, the solubility product constants, and some challenging ones that I ran across and I wanted to treat separately. So I hope you found this helpful. If you have any questions, send them to me. And in the meantime, happy studying and have a great day.